going to be introducing the gacnn. This will be what the genetic algorithm, or GA, is, and how GA can be used to optimize CNNs, or convolutional neural networks. For an outline, there will be some background into the convolutional neural network, or CNN, the genetic algorithm, or GA, hyperparameter optimization, HPO, and early stopping, or stopping criterion. Then some motivations on the significance of the HPO, some problem statement. Additionally, there is the formulation of the problem for GA, which one part is the binary layer network, some results for the MNIST dataset, as well as the DeepSeek dataset. For some necessary background information on CNN, they can classify images with high accuracy. It is a network comprised of layers that are linked together, in this case, serially. There's an input, multiple types of layers in between, and the output. The input is an image to classify, and the output is the class. For these different kinds of layers that are considered in this GACNN case, there's the convolution layer. This is the basic layer. This reduces the dimension, extracts features. There's the rectified linear unit layer, or ReLU. This is a threshold function which changes inputs that are less than 0 to 0. There's batch normalization, which normalizes inputs to the mini batch. There's some pooling layers. They are average pooling and max pooling. This will also reduce the dimension, and then it can be either a maximum or average in terms of the pooling. Fully connected layer, this will also reduce the dimension, but to 1 times 1 times the class, so this is 3-dimensional. There's a softmax layer. This will normalize the output from the fully connected layer to somewhere in between 0 and 1, like a probability. And then last, there's the dropout layer, and this will just drop out values in between. That reduces the complexity. For the genetic algorithm, this is a global optimization solver, which means that there are distributed local solvers. And this can be done in parallel. Each local solver can be done independently. And this is an evolutionary algorithm, which means that there are generations, and only the best solvers survive these generations. So out of these local solvers, you're only going to have a few that are the best, that are the elites, that survive to the next generation. And in between these generations, the mutations can occur, like evolution. And one of the benefits is you don't need initial inputs, so you can just randomly put these local solvers and have the algorithm start from there. Additionally, benefits of the genetic algorithm are that you can have any constraints and any objective function. These can be functional, as in any function, nonlinear, or integer constraints or objective function. This works well in large spaces because there is randomness, and you can use many variables and variable types like integers, binary variables, continuous variables, all mixed together. Next is the hyperparameter optimization. This is what GA is doing to optimize the CNN. And to optimize the objective function, in this case training a CNN of some hyperparameters, HI, and what's returned is higher accuracy. So these hyperparameters could be training variables like learning rate, layer variables like the pooling size or the convolutional filter size or number of filters, and the actual layers you used, like a convolutional layer, a pooling layer. One of the methods for gacnn is early stopping. This is where the CNN training can be stopped early or before fully trained. Now, this is based on some criteria, which is some function or time, such as only training for some number of epochs or some number of seconds. And the goal here is to increase the accuracy by saving time on each of the training. Some motivations for this gacnn are the limitations to existing methods for freedom in the network creation, specifically freeform layers. So this would be layers anywhere in the network, whichever kind of layers, and layer parameters, as well as the layers used. So this is creation of the network, and there can be layers anywhere and any layers used. Also, lower runtime and less resources. Existing methods can take days to run. So here, a problem statement would be to construct a genetic algorithm definition that accommodates some freeform network structure, layer parameters at the same time as the network structure, can run fast, so this can generate a CNN fast in terms of hours, maybe minutes, and it has decent accuracy. The method for allocating the layers in the gacnn is the binary layering method. So now GA communicates in variables, so the layers must be translated into variables. So here, each layer is a binary variable, and there are possible layers A to F. So here convolution is A, dropout is F. This can be represented by one group, and these groups can be strung together for many possible layers in a network for scalability. The process of creating a network here is to append the groups together. So there would be n groups of possible layers. And if this was multiplied by the binary variables that are the layer is there or the layer is not there, the result would be only the layers that the genetic algorithm wanted to assign. And with these layers, the network can be built. For mixed layers and layer variables, the binary layering method will allocate the layers, and then at the same time the layer variables are assigned within the CNN, such as convolutional filter size, the number of filters, the pooling size, and the dropout probability. This is all done while meeting the network constraints. For the metaparameters, which are parameters above the genetic algorithm that are not changed during the algorithm runtime, are population size. This is the number of local solvers. The more of these, the larger the search space for possible solution that is better. The crossover or mutation rate is 90%. Because of the large search space, this allows for more randomness. The percent of training data, which is the subset of the data set, and this is 20 to 25%, which increases the speed because each of the solvers does not need to use the entire training set. Training epochs, which is the early stopping, which is set to 3 for speed. The groups of layers are set to 10 for possible 60 total layers in the CNN. The elite count is set to 10, or 10% of the population size. This is to avoid local minima. The process of generating results is to create a reduced data set, which is the 20-25% for runtime speed. Run the genetic algorithm to optimize the layers and layer parameters. This can be run until 70% or higher accuracy, or progress has been stopped, shown here. And then, after this, use the full data set and then fully train this network of layers that has been output by the gacnn. And the result of this training would be the final accuracy. On the bottom right is a picture of during the runtime. A solution farther left, or negative, is represented by a higher accuracy in the local solver solution. And the vertical is the number of solvers that have this accuracy solution. So the elites would be the best solutions for this left, and there would only be a few of them. So it's not very high. Whereas on the right, the lower accurate solution, there are many of them. In the image on the top right is once no progress is being made and the runtime can be stopped because all of the solvers are in a random distribution and there are no pronounced elites. To test the gacnn, one data set is used that is very simple to run and get high accuracy with, is the MNIST dataset, which is of handwriting images of numbers. There are 10 classes from 0 to 9, one for each number. Here is the gacnn generated from the MNIST dataset. These are all of the layers and the layer parameters. There were 33 layers in total, which is 29 out of the 60 possible, as well as 4 layers for the input and output. The final layer size is 2 by 2, down from 28 by 28. This meets the network constraints for being feasible, as the dimensions are greater than 0. This takes 30 seconds on one core, 15 generations, and it trains in a few seconds. Here's an image showing the training progress as it reaches 100% accuracy in a few seconds of training. And this is the confusion matrix of the test data showing 100% accuracy in the classes. During the result process, this image shows the flow chart where a dataset is input, the generations are created, parameters assigned, constraints are then tested. If they are not passed, this local solver fails and is not usable. If the constraints pass, then the solver is usable and the network is trained. Then, with the result of that, check requirements such as minimum accuracy required. If this is not meeting the requirement, keep the best solution for the elites in the next generation. Otherwise, if the requirements are fulfilled, then output the optimized network, stop the program from running. Additional results for another data set include the DeepSig Radio ML 2018 dataset, which includes 24 modulation types across ranging SNR from negative 20 dB to 16 in this plot. The results show the blue line of proposed gacnn attaining an accuracy on the y-axis, average accuracy for each SNR, versus the baseline, which is used in reference 12, over-the-air deep learning based radio signal classification. And both of these models use the base CNN layers that were explained. However, higher accuracy has been achieved using non-base layer CNNs such as ResNet and skip connections. This proposed is a gacnn that was generated from no starting network and resulted in a network that can classify at this accuracy. Additionally, the network has 39 layers, trains in 25 minutes, 0.8% of the dataset was used to generate it, over 14 generations and 6 hours.